Hello and welcome to Control F, the National Security Institute's Cyber and Tech Center's new podcast that will feature special series on topics ranging from deep dives into emerging technologies, the ever evolving tech policy landscape, and uncovering the scientific breakthroughs that are shaping our world. Today, I'm excited to kick off our very first series in the Control F podcast, Unleashing Innovation, Navigating Game Changing Technologies. In this first series, which will publish new episodes every 2 weeks throughout this summer, we will explore emerging game-changing technology capabilities like accelerated computing, generative AI, and cloud and edge computing. We'll look at the technology itself and its business and economic and national security implications. We'll feature leading technical experts in a given field, as well as the investors supporting the development of these critical and innovative technologies. So today, we're going to talk about the game-changing potential of accelerated computing. We have Dr. Eric Breckenfeld, the Director of Technology Policy at Nvidia, and Gilman Louie, CEO and co-founder of America's Frontier Fund. Eric is an expert in semiconductors, focused primarily on the impact of computing and AI technologies on American competitiveness and security. He knows that it's crucial for the U.S. to lead in innovation in foundational technologies, including electronic hardware and circuit design and their application. He's worked as a technical consultant, policy advisor, scientific researcher, and stakeholder advocate. Gilman has over 30 years of experience in national security and investments. He started in video game design, designing one of my favorite games growing up, Falcon, the F-16 simulator. He's also the guy who brought us Tetris from out of the Soviet Union and brought it to America. He's taken his passion for technology and innovation to make a lasting positive impact on U.S. national security. He's also served as an early CEO of In-Q-Tel, an expert on the Defense Innovation Board, and as a commissioner on the National Security Commission on Artificial Intelligence. So let's get rolling. Let's jump in right with you, Eric. Eric, talk to us about accelerated computing. What is it? How does it work? What's a CPU? What's a GPU? And why do we care about accelerated computing in the context of modern computing, AI, and the like?
Yeah, great question, Jamil. Big question also. So I'll try to nibble at it around the edges because I think that the sort of broad question of what is accelerated computing and why is it important, can definitely dominate an entire 90-minute conversation. So just
Cool.
very broadly, really in the context of the technology we're looking at today, which is a lot of deep learning, AI, generative AI, large language model, that kind of framework, and what it borrows from NVIDIA's history, the graphics and graphical computing space. Maybe let's look at it in that context first. So really what
Yeah.
accelerated computing refers to is knowing what kind of computing workload you're going to have and then designing hardware that's especially efficient at processing that kind of workload. And so there's lots of different accelerators. You can think of accelerators that are good at cryptography, accelerators that are good at taking analog signals, RF, and turning them into digital signals. These are all accelerators. But for the purposes of what we're talking about here today, there's really one or two accelerator classes that we're really interested in. The first was the graphics processing unit, the GPU. That was,
Okay.
you can kind of go back in the history of, maybe not such a coincidence, but gaming really arose out of gaming and the need to design computing hardware components that were good at synthesizing graphics and really moving pixels around on a screen, right? That's what graphics is. And going into the mid 90s, you started to have a demand on graphical interfaces that was slowing down CPUs, the central processing unit. This is the all-purpose, central brain of your computer that can handle lots of different tasks. Well, in the
Yeah.
past, long in the past, to 30 years ago or so, a lot of the graphics were handled just at the CPU by the general purpose processor. But as the demands in graphics got larger and larger, and then there's a couple of video games that were very formative for myself. These were games like Doom, games like Unreal Tournament, around just the end of the 90s. That's when the graphics demand started to get so onerous that it was slowing down the
Mm.
central processing unit trying to process all those graphics. And that's why there was an emergence of, actually, I don't know what exactly the full number is, but it was around 100 different companies in the mid 90s were trying to stand up GPU architectures to say, we're going to design a chip that lives next to your CPU, and the only thing it does is process graphics, which really is just a lot of matrix multiplication, right? It's
Okay.
figuring out how you rotate pixels first in 2D and then in 3D space. And so that's
Okay.
matrix multiplication, really. And so designing a chip that really just did that and then making it better, making it more efficient, making it use less energy, being able to process more and more data in parallel. That's one big difference as well, by the way. The CPU tends to have a small number of cores. GPU has an enormously large number of cores that all run in parallel. Now, the operations they do are somewhat simple compared to what the CPU is capable of doing, but it can do many more of them in parallel. And so that's
Got
an
it.
early example of an accelerator, right? A graphics accelerator. I want to accelerate a part of my workload and do it as efficiently as I possibly can. Graphics
Yeah.
was the first example.
Awesome. And look, I want to talk a lot more about how GPUs work and how they compare to CPUs and these new tensor processing units. And there's a lot of innovation going on in this space. But before I do that, I want to turn to you, Gilman. So, Gilman, you've spent a lifetime developing high end graphic software, high end capabilities, but you've spent the bulk of your career recently investing in this space. And one of the focus areas for your new investment firm, the America's Frontier Fund, is in semiconductor technology specifically, right? And look, we know that advancements in this domain play a huge role in modern innovation in America, in allied countries, in our defense sector as well. And look, accelerated computing is obviously a key part of that story. Can you talk to us about the importance of semiconductors themselves, where we stand today in the production of semiconductors here in America? Why is it so important? Why do we care? I mean, we know the government's investing billions of dollars, the CHIPS Act, right? Why is it critical that America remains a leader in this space? And actually works with partners not just to continue to design these chips, but actually produce them.
Well, if you think about where we've come from, right? The kind of the last industrial era around the internet information was our ability to process kind of digital information. And we're about ready to launch into the next industrial revolution. And that's where it's not just the digital components, but where digital and physical worlds actually meet up together. So you're thinking about things like advanced manufacturing, 6G communications, digital critical infrastructure, space and satellites, food production, synthetic biology. All of these things require compute. So at the core of all of these new threads of massive changes, and even in things like how we think about energy and in the future of how computing is going perhaps down even the quantum lane, it starts with our ability to process massive amounts of information around chip designs. And the reality is the speed of the chip equals the energy being consumed equals the power of what you can do. So those
Right.
who have the most powerful chips have a significant strategic advantage of those who don't. And so from a national security, financial security, from an economic security kind of framework, microelectronics is at the heart of many of the things that we are working on. It is why, if you think about the competition particularly between the United States and China, right?
Mm.
A bulk of the conversation and competition revolves around chips. And when we hear things like, small yards, high fences, it's really about access to the most important high-speed chips that drives our AI, drives our national security, drives our ability to actually industrialize around knowledge and our ability to process knowledge. So
Got it. Yeah.
for us, it's critical, it's foundational.
Why? So let me ask you this question, Gilman. Why have we gotten in this place that we are today? So as I hear the story, and tell me if this is right or wrong, the story I hear is that we generally in America today is we innovate dramatically in chips. We build great chip designs. We're great at creating the concept behind them, but then we export the production of them overseas, predominantly to Taiwan, which obviously is under significant threat from China. And the national security community has been talking about that for a while, and the threat seems to be growing. But there are these commodity chips now that are being made in China, right? These larger nanometer chips, those smaller, more 3 and 4 nanometer chips that are at the cutting edge, and they'll be smaller even more soon, even more in the near future. But why is it that we don't produce chips in America today? Do we need to be doing that? And if so, are we spending enough on that? We've billions of dollars in the bipartisan infrastructure bill, the CHIPS Act, and the like. Is it enough? Do we need to be doing more? Are allies part of the solution? What's the answer here?
Yeah, as Eric said, that's a very big series of questions. I'll try to unpack it. Right. There was a whole trend in the 90s about efficient manufacturing, right? It's streamlining, just in time, lean manufacturing. We did it with our chips, we did it with our airplanes, we did it with our cars, right? We said there are cheaper places we can manufacture,
right,
where we have greater access to labor. Two is, if it's messy and dirty, involves chemicals and other things, we can push that problem to make it somebody else's problem. And we're just going to focus in on the very tippy point of the pyramid, which is the intellectual property creation and IP.
right.
Now, as we kept making that system more efficient, we in effect made the system more brittle. So we became more and more reliant on these supply chains, which we no longer had total control of. Now, Taiwan, on the other hand, said, hey, look, like, we're a little island, right? We're, there's only so many things we can do, but, we think we can revolutionize how we think about manufacturing of chips, right? And we're just going to focus our energy around that. We're going to build out fabs. We're going to have a infrastructure, power of water to support the fabrication of chips. We're going to have thousands of suppliers that will become our part of the supply chains, and Taiwan Inc. will be chips for the world.
And they did it.
And they did it, right? And a lot of people said they couldn't do it, and they did it, right? Hard work, great innovators, entrepreneurs, right? Country, national priority, they made it happen.
Generation-long investment in workforce as well.
Exactly, right? I mean, if you think of the top 4 universities in Taiwan, they drive 70%, right, of their graduates go to TSMC, which is the #1 manufacturer of chips in the world, right? Their best talent does that. Unfortunately, they're 110 miles off the shores of China, and the PRC
party-controlled China.
Yeah, exactly. And the challenge with that is, if hostilities breaks out, it puts somewhere in the neighborhood of 10 to 20% of the world's GDP at risk, because that's where all of our most advanced chip manufacturing take place. So we kind of did it to ourselves. Now we're trying to undo it. We're trying to onshore many of the capabilities. We're trying to friend-shore, bring our allies in. But, it's a long road, because that ecosystem took decades to build, and it's not something that we're going to be able to reconstruct overnight. So we got to continue to partner with Taiwan. We need to begin to onshore expertise. But I think Eric put his finger right on it. Our #1 challenge is, the lack of talent. And it's not just STEM talent. I'm talking about the talent to build these fabs, to run these fabs. It's the entire kind of ecosystems, the equipment side. We need to rethink it from the beginning, and it'll take us, if we're lucky, a decade to get there.
And I think the Taiwan story is a vindication that if you make these investments and you have a long-term strategic goal in mind, you can be successful. But it also is a warning. This is what it takes to be successful, right? This is not CHIPS Act is 5 years. Taiwan did not establish themselves in 5 years. It took a long time. And so, it's a vindication, but it's a warning. Hey, this is not some small lift. It takes a sustained effort over a long period of time.
And let me add to what Eric said, and this is another important concept, right?
Please.
It was the will of the people and the will of the nation, right? It was both. And we have a term, industrial policy, right? Our industrial policy right now, chips is kind of the first part, but we have a long ways to go to be able to invest, because you cannot rely on the stock market to build out that critical deep infrastructure to build these kinds of plants and facilities, because economically doesn't do the quarterly returns. So we're going to have to find out other financial models that support that deep investment, and that includes nation state investment.
So there's been a lot of talk about this, Gilman, and I want to get your thoughts on this, Eric, too, because you talked about workforce. I want to dive into that, but real quick on this point about infrastructure investment. I come from the conservative school of thought, and there's a lot of sort of conservatives who say, look, industrial policy is a bad idea. It's a variant on socialism, right? But the truth, Gilman, and tell me if this is right, we've had industrial policy in this country forever. In fact, the bulk of our major innovations, telecom, space industry, right, modern technologies come out of government-seeded research funding, right? That
Silicon
sort of
Valley was in many ways founded on DARPA investments many decades
yeah,
ago.
yeah, the Palo
Yeah.
Alto Research Center, right? Park, right? Xerox Park, right? Um, I mean, so this story isn't really true, right? Now, look, the government investment in our context may be different. It's not picking winners and losers, right? It's creating that seed money, that early research money. It's creating the right incentives, the right tax incentives, right? The right labor incentives, right? But it's the idea that we don't believe in industrial policy. That's am I right? I mean, Gilman, Eric, tell me if I'm right about this.
I think it's whose version of industrial policy that you believe in versus not believe in.
Yeah.
But as you pointed out, look, we won World War II off of industrial policy.
Yes.
We outmanufacture the access, right? Orders of magnitude, right? We can
Right.
produce planes, ships, right? Aircraft faster than anybody else in the world. Industrial policy got us to the moon. Right. Silicon Valley was built off of radar investments that were done in World War II that led to multiple generations of engineers that now leads to great companies like Nvidia and Intel and Apple and all the other companies that are happening in Silicon Valley. And industrial policy got us the internet, right? Because of the original investment in ARPANET and BBN.
Yeah.
I think the
Started
real
at
issue
UCLA.
I think the real issue is which version of industrial policy. And I think some of us don't want the Chinese version, which is picking a winner, like a Huawei to be the national champion at
Right.
all expense. We believe in competition. I think there's a role for industrial policy in a competitive environment where the best wins.
Yes.
But the cost of capital is low enough so that we can be competitive with other nation states who give away their capital for free.
Yeah, I
So
think I
let's
totally
yeah.
agree. I'll just one way of looking at it, I think, is exactly making it work, doing our version that works for us, and then asking what's the end state. The end state of our
Yeah.
investments in, say, the internet wasn't some technology that in a command and control sense the U.S. government owns and controls. That was not the desired end state. You do industrial policy in a small scale, or even just take CHIPS Act. The goal of the CHIPS Act isn't how do we get to a state where we make a $50 billion injection into the US semiconductor industry every 5 years? That is not the end state we want to get to. And so
Right.
the US industrial policy is you nurture something either when it's in an early state or when there are these marginal moments where we know there's a lot of global capacity that's going to be stood up over the next 10 years. Can we make investments on the margins to encourage that as much as possible to be in the US? Right? Not that we have to do that always, because the end state, just as Gilman said, is how do you end up with companies who can be competitive on the global stage and not need constant injections of cash, right?
Yeah.
That's the end state. And I think that's what's different about industrial policy that works for the US and is compatible with our system versus how it's done elsewhere.
Yeah. Now, Eric, you mentioned something really important earlier, which was this issue of workforce, right? And there's been a lot of talk, by politicians in Washington and people in the states and companies. Everyone in America agrees we need a better STEM pipeline. We need more STEM talent. We need to be getting kids up on all these issues. You've got a PhD from University of Illinois at Urbana-Champaign, right, in material engineering, material science. Talk to us about what our STEM pipeline looks like. Are we doing enough? Do we need to do more? I mean, accelerated computing is a product of people like you, right, here in the United States, learning the stuff, creating the technology, creating the capability. But as Gilman points out, right, not only do we not necessarily are we creating the IP pipeline of talent, we're not creating the engineering core build it talent in this country either, right? Are we gonna get there? Are we gonna catch up? Is part of the answer, God forbid I say it, immigration? I mean, imagine that. Eric, what do you think?
Yeah, there was actually a report released about a year ago by the Semiconductor Industry Association, which I helped work on when I was there. Although it
You
was
were a
released
fellow
after
there, right?
I
Yeah.
left. I was
Yeah,
there
postdoc
for
fellow.
about a year and a half, and then so it released just after I left. I helped work on it a little bit, but they work with Oxford Economics to do a projection until 2030. So this was a look of 2023 to 2030. How do we expect employment in this sector to grow? And it's manufacturing and design in the United States specifically. And so what they estimated is by 2023 to 2030, we're looking at a growth of about 100,000 jobs. That includes manufacturing at the technician level, at the engineer level, and then also in the design space, right? So this is computer scientists, computer engineers, these sorts of folks. And of that 100,000 job growth, based on who is currently in the pipeline, and if you look at graduation rates and what percentage of graduates typically go to the semiconductor industry, you can do some modeling in this. And we found that about 60,000 of that 100,000 are, in a sense, missing from the pipeline. And there's a few reasons for that, and you can actually break it out into. I would encourage folks to go to semiconductors.org, take a look at the study there, because the numbers are there plainly. But really, the purpose of the study is just to put some bounds on these numbers, because you hear lots of different numbers. But you can kind of break it into three categories of workers who are missing. And of that 60,000 missing, it's almost cleanly based on the modeling, which was very coincidentally beneficial for talking about it. It's about one third. It's about 20,000 missing from three different categories. One of them is technicians who operate the fab itself, and typically operate at the associate's degree level or below. And so it could be a 2-year degree, it could be even just like a 6-month certificate. But it's people who actually operate the making in the fab. This is, when I look at the investment Intel is making in Ohio, that's who needs to go there, right?
So
the
we
other
have a gap
1/3
there. You're saying we already have a
there's
gap.
a gap there. There's about 20,000 missing technicians in the pipeline. There's about 20,000 missing engineers who are mostly at the master's degree level, but then there's some bachelor's and PhD. And then there's about 20,000 missing designers, computer scientists, computer engineers focusing on design. I think the greatest challenge in those three categories, as I observe, I think the technicians we need, the pipelines are there, but investments need to be made. If you look at where these people work, they typically get a job in a zip code in or adjacent to where they got their degree. So they need to be regionally targeted. This is community colleges, this is trade schools. I think some of that's starting to happen, but I do think the pipelines are there, because in order to get someone to get a technical degree, you need to persuade them that a job is on the other end of that degree. In order to get someone to get a master's degree or PhD in engineering, you need to reach out to them in 8th grade, in high school, right?
Really?
And convince them that this is the kind of path they want. You don't go to someone who's a junior in undergrad and say, hey, have you ever thought of getting a PhD? If they've thought about it by then, they were thinking about it, at least considering a career in STEM much, much earlier in their educational career.
Wow.
This is why the greatest challenge is this engineering and PhD track. There's two reasons for it. One is that if you want to do it domestically, this is what Taiwan did successfully. It starts in primary education. It starts so early. It is not something you go to undergrads and try to persuade them to do. You need to have already started to make the case earlier in their life. The other thing, towards your very pointed question, Jamil, is more than half of graduates in, let's take electrical engineering as an example, at the master's degree level are international students. And it's worse than that for PhD. Right. And if I look at the long-term retention rates of someone with a STEM master's degree in the US, it's about 20% retention. That's at the 10-year mark.
That's because our system literally says to these people, hey, we'll take the world's best and brightest, we'll bring into our schools, we'll train them in the best institutions of higher education in the world, and then we'll tell you have to go home to build your company.
You have to enter
overseas.
a lottery. I mean, I don't know if I look at what the H-1B success rates were last year. It was terrible. It was less than 20%. And so you have to enter a lottery, and it's not a sensible system.
The way you should think about it is the U.S. has a strategic advantage over our competitor nations because people want to come here.
Yeah, they don't want to build their company in Beijing. They want to build their company in America.
You make a country that's good to live in, good to build a business in.
Their very best want to come here. Their very best to be educated here, to work in our workforce. I mean, Silicon Valley, right? If you look at Silicon Valley, the people of color run the valley. And it's because of the talent that we've been able to attract and retain from the best universities. Unfortunately, our immigration policy has got lost into a political debate that is not consistent where we need to go as a nation. Eric talked about the workforce, particularly on the high end. I totally agree with him. You look at the production rate of the best talent that we have of our engineering schools. We're not having enough people getting into those schools to come out of the schools to lead to productive positions. But equally, on the other side, and this is not just the technicians, but the plumbers, the welders, the electricians, the people who are going to service the equipment, right? We have lost our trade base. And so we also need to build out the trades. That means strengthening up how we had to rethink the unions and how they have a role in playing out on the workforce development. And so we need an end-to-end workforce strategy. Now, there is a reason why workforce is such a big focus for commerce right now, because they understand, right, the challenges that we're having in Arizona and in Ohio and Texas, right? Yes, some of it's regulatory, but a lot of it's workforce. And so, and it's not just to the big companies, right? It's not just to the Nvidias of the world and the Intels of the world and the Microns of the world. It's also to all those medium and smaller companies which service as the supply chains that services up into those design houses and the fabrication capabilities, the assembly, right? Great, you can produce the chips, but then if you're going to be assembling things offshore, you're back in the same position again. So we need a complete labor force, and we have to get the entire country involved and not just the coast.
Yeah, yeah. So, Eric, if we build out this labor force that you and Gilman are talking about, and we're able to put this labor force to work, whether it's through immigration, right, through education in our schools, ultimately getting down to that STEM pipeline you're talking about, and they're creating this innovation. What is the next generation? So GPUs are right now all the rage, right? There's been talk, I know, about field programmable gate arrays, FPGAs. We've long had ASICs, right? There's talk about these tensor processing units, TPUs, right? What's the next sort of thing in accelerated computing, and what's its application? I mean, I know it's great, but GPUs are great for graphics. Their massive parallelism that you described makes them great for AI, right? And these AI applications. Is AI the future? And if so, is this the current architecture? What's sort of what's on the edge? I mean, Nvidia is one of the leading companies in this space. What's the next thing we should be shooting at, and how do we get that workforce that's built around that?
Yeah, I will try to frame it in a context that Gilman mentioned earlier, actually, and it's in the context of what is sort of this new, you can call it a new industrial revolution for maybe lack of a better term, and what it is, what the next thing is, or what is this application of this big thing we call AI for something other than just a text block I chat into that gives me paragraphs or helps me write undergraduate essays or something, right? Like it has to be more than that. I think that's well felt. It's the infusion of intelligence in a general sense into many of our systems of operation. This is manufacturing, this is healthcare, it's user-facing things like at patient healthcare. It's questions of bedside manner and analytics that can be assistant tools for doctors so that I can take one surgeon and then I can make them as productive as multiple, because all the things that are on their plate that aren't just doing surgery, I can make easier, right? So it's infusing intelligence into that, but it's infusing intelligence into manufacturing. It's infusing intelligence into systems of sensors. And so then I keep saying this word intelligence. What do we mean by that? This thing I say it is intelligence, like, what am I including in that definition? And I think the best way to look at it, and then I'll talk on the architecture side, because I do have what I think is an important answer to that question. Intelligence, and this is true for biological intelligence or for machine intelligence, is the creation of a model of the many things that you sense. A biological system is a multi-sensor system. I can hear things, I see things, I touch things. As I'm an infant and I grow into a small child and then I grow into an adult, I'm training and I'm building a model of the world. The things that you see around your room aren't real things. These are collections of atoms and molecules. But you have an internal model in your brain that was trained on the data you collected based on sensors, mostly in your face and fingertips, right? Intelligence is a condensed down model of reality. It lives in your brain, lives in biological brains. We can also make a synthetic version of this. This is what's happening in data centers where we're feeding in text. We're making a pared down model. You can think of it as a sort of a compression. I'm taking reality and I'm compressing it down into a model. And that model is meant to be functional. So it's smaller. All the data of reality is huge. The model is only 100 gigabytes, right? That's a lot smaller than the data of all of the reality that I observe. And so you can think of intelligence as sort of the ultimate form of compression. I'm taking all this data, I'm compressing it into a model. Now, how do I take that model, whatever it is, and apply it to certain areas, manufacturing, healthcare? And then maybe I want different models, right? Maybe feeding in different sorts of data or weighting them differently, things like that. Now,
Yep.
where does that happen? Well, the training, and maybe to some degree the inferencing of these models, the training happens in a data center. And so what is the next thing? Moore's law was an answer to how much compute power can I possibly fit in one area on a silicon wafer. And
Right.
I want more transistors. I want them to be closer together, because closer together means lower energy
Faster.
to do the compute
Yeah.
operation. It means I can do it at higher frequencies, all those benefits, although that actually fell off a little while ago. But it did mean that for a while. Okay, so Moore's law for the chip was a question of, on a single piece of silicon, how much compute can I get on that plane, right? There is a similar question that's in the process of being answered right now in a single data center. How much compute can I possibly get in there? Because it's more than just a question of how much I fit on a chip. It's a question of bringing, in the same way that when I want to make everything on a chip smaller, I want to bring everything in a data center closer together. I want to put what are called DPUs, data processing units. The way I move data around in a data center consumes energy, and it's inefficient, and that efficiency can be improved.
Yeah.
I'll just give one example.
Power,
Since I'm from
space, and
Nvidia,
cooling.
I'll give a product pitch here, but Jensen just debuted our Blackwell chip at GTC, and you hear lots of different
We
terms.
saw that thing. It's big, right?
Absolutely. The chip is
Yeah.
big, and then it goes in a data center, and we see these questions. It's 5 times more efficient, but it's also 30 times more efficient. Like, what does that mean? So if you go down and you look at, and this is the answer of what's next. You go down and look at the chip itself, the Blackwell chip. Compared to the B100 is Blackwell, so compared to Hopper, the H100, if I just look at the silicon, just the chip next to each other, it's about twice as efficient, right? It's about twice as much throughput, right? Sounds a lot smaller than these like 30x numbers that Jensen's saying. So where does that all come from? And so a lot of that comes from questions of architecture and then integration into the data center. The architecture is different because I handle numbers differently, because I know that AI applications don't need high precision in their numbers. So think about it like this. In the model, does the output of the model care if one of the, whatever 100 billion parameters is a 4 instead of a 5, or maybe those are basically the same number? Well, if those are basically the same number, then I don't need to use 8 bits to represent a number. I can just use 4. And the fewer bits I use to represent an individual number means I can have models that are larger, that take less energy to train. So
it seems counterintuitive,
Blackwell,
right? It seems counterintuitive.
it does.
Using
That I go to
the
lower
less-
resolution,
But
but I get.
That's because you're an old person. You grew up on complex computing.
So we're going back.
We're
And
going back to
more,
rest. We're going
to more
smaller.
complex instruction sets too, because you bake in more linear algebra operations into your
Exactly.
instruction set, because if you control the full stack of software, you know what applications are coming through, and you can see, hey, these sets of linear algebra operations always go one after another, and in between each, they're reading and writing from memory, but like that costs energy. Instead of doing that, how about I just do one big operation and I just read and write at the end, right?
Yeah.
And I cut out all these steps. So I take out what's called the memory overhead. So that's happening at the chip level. But then also how the data moves around the data center. So Blackwell to Hopper, it's 2x at the silicon. But when I look at all of the networking chips that the Blackwell system uses, that gets me from a 2x at the chip level to a 30x difference at the data center level. But think about how you as a user interact with the chips. You're not plugging it to one chip. You're sending your queries to a data center. So that's the 30x is what matters. And that is a data center question.
I want to make sure I understand this right. So what you're telling me is Moore's law is really relevant to that chip and its efficiency and making it faster and better and whatever. Great. But if you make the transport between chips faster, because the way we're delivering data and the need for parallelism and the like, that actually has a bigger effect. Is this Breckenfeld's law? Like what are we talking about here? Like
they're actually calling it. Some people are calling it Jensen's law, but okay. we rode Moore's law almost to the end. I mean, we can argue what the end of Moore's law is, but eventually we're not that far away from one single silicon atom. If I look at what a unit cell, silicon unit cell is only maybe 2 more generations beyond what we're at. That's a single silicon atom. So it ends by the laws of physics eventually, maybe by the laws of economics before then. But once you've done that, once you've exhausted what you can do with Moore's law, then the question is, where the other areas we can get improvements from. Improvements in speed, improvements in energy efficiency. The H100 data center to the B100 data center, I've reduced my energy to quarter the energy use for the same model. So if I train GPT,
it's more
it's more energy
environmentally
efficient, and it has higher throughput. It has 30 times higher throughput, and it uses 1/4 of the energy. And this is a change in packaging. This is a change in specialized chips that live at the interfaces, right? Imagine I have these huge racks of chips. Those racks need to talk to other racks. What chips govern those communications? That's the data processing chips. Those are also accelerators, and they are accelerators for moving around large amounts of data inside a data center.
Yeah,
And
so
so,
yeah.
I think Eric points out, right, that the next series of innovations are all around innovations of the complete system. Now we start with the chip, then we talked about stacking chips, right? Interfaces of chips, how to reduce the amount of swapping between compute and memory, between the GPU, the buffers, and the CPUs, how to reduce latency across the different servers on the server racks, how to reduce long-range latency between the cloud and the device, what's onboard compute, offboard compute. Not to mention innovations in the way we think about compute in general, right? At some point, quantum computing, whether it be the sloppy kind of version we're kind of playing with today, or ultimately, where we actually have really true, well, I'll just say simply digital versions of quantum computing in the next decade or so. All of those things are colliding. Simultaneously, as we reduce down power consumption, remember I said power equals compute, right? Power also matters. So sources of power matters, right? So if we can produce more power cleaner and more cheaply for the data centers, as data centers become more efficient, now I got more power that I can deliver to my data centers that's generating less heat, right? That's in smaller spaces, that are more distributed across the country, that doesn't rely on the challenges of the grid. All of that is a part of rebuilding out our digital infrastructure. And so cloud, compute, AI, intelligence, right? Telecommunications are all part of what we're trying to build out, which is this digital infrastructure that supports this next industrial build out of the world. And so that's why when you unpack it all, what Eric and Jensen are doing is so fundamental, right? To whether or not you're a player, you're a leader, or you're left behind, is your ability not only to get access to those chips and those server designs and that infrastructure, but also your ability to leverage it and build the next generation applications that live above it.
And I think Gilman actually touched on a really important point, which is the point of energy. I'll just mention really quickly, because it's part of the conversation right now, that are we concerned about the growing energy use of these training models, these chips, these systems, right? I mean, and obviously Nvidia is, of course, the single figure of merit that we pursue is energy efficiency. And that's not an AI question. I mean, that's been true. Accelerators need to be as efficient as possible. That's a graphics question as well. I mean, so improving efficiency has been at the heart of Nvidia's architectures since the beginning.
And it's not, to be clear, it's not an ESG thing. This is because it's literally what makes you money.
This is the value proposition of our chip. Indeed, we don't need the U.S. government to say your chips need to be more efficient. We agree. That's what our R&D is entirely pointed at. So yes, we totally agree on that. But I would also just note on the energy question, from let's say the 2010s to 2020s, there was this emerging idea of what they called not a virtuous cycle, a nexus, an energy, water, food nexus, when we think about sustainability. And you have to think about these three things kind of in combination. You can't just improve one. You have to consider energy, water, and food all as a connected system. I think what we're going into the 2020s is what I've heard called the nexus, but I actually don't quite agree. And I think of it more as a virtuous cycle. But it's the compute, the data center or the intelligence, the hardware, the chips, and the energy. There's a nexus there. I actually don't agree that it's a nexus. I actually would call it a virtuous cycle. And here's what I mean by that is right now, the idea in people's head is energy plus chips equals AI, right? AI consumes these things. It consumes energy. It consumes hardware. We need to feed more hardware into this growing hunger for AI. I think that there is a a mastery of a virtuous cycle that needs to happen in order to unlock this next revolution, and it is to feed intelligence back into those systems to make them more efficient. So yes, AI consumes energy, and if we master the virtuous cycle, AI improves the efficiency of our energy system.
Meaning it'll consume less energy.
To consume, exactly. It makes energy sources cleaner. It makes the distribution more efficient. We can use it in the discovery of new energy sources, or just as an example, Lawrence Livermore National Ignition Facility used machine learning empowered simulation for their fusion ignition that they successfully did a few months back, right? And so this is what I mean by AI enhances energy, and it needs to, because what we can't have is runaway energy. And it's the same thing for chips. And by the way, Nvidia has their own platform called Chip Nemo, which is where we took all of our design going back into the 90s, loaded it into a large language model, which we now use as an assistant for our engineers to make chips more efficient, right? And so I wouldn't look at it like the intelligence consumes resources. That is true, but if we master this virtuous cycle, it also improves those original sources. And so it's not just this runaway energy curve, right? It makes everything more efficient as well. And that's what we're trying to master right now.
And we're so far off from an optimized system, right? I mean, think about how many watts your brain actually uses. It's a handful of watts. We're not talking gigabytes and megawatts, right? It's a handful of watts. So in this march of AI, as great as generative AI is in this current iterations, we're a long ways from that, model that says we're at a place where compute, right, it's challenging biological computing. In some areas it does, right? But the real challenge is, how do you bring those two systems together for increased productivity? How do you team the intelligence of machines, the intelligence of humans, the environmental systems that both need to coexist and optimize for end results? And if we do that, we kind of think about the problem differently. It kind of even goes back to the education problem, right? We make certain assumptions of what the input has to be to get you one productive engineer that can do design. But that person may be completely different in the future when that person is teamed with AI, machine algorithms, and digital twins, where we can actually use the models to reinforce and create this virtuous cycle that Eric's been talking about, right? Think about it. Generative AI proposes a hypothetical solution. It's tested and validated against a digital twin of the world, of the physical world it needs to be operated. And it senses the results, the actual results of the thing in the real world. It feeds back to the model, refines the model, re-optimizes it again, and runs 1 billion simulations in the meantime, right, to turn the little dials to make it better. That's the world we're about ready to enter into. And that's a completely different world than anything that came before it.
Yeah. And I'm not even sure that's an industrial revolution. That's some sort of revolution, but it might be different than even industrial. So Gilman, so talk to me about, so we've heard a lot from Eric about how Nvidia is thinking about the space and how transport matters. And as you're an investor in this domain, right, there's a lot of things you could be investing in, right? Talk to us about how you're thinking about your investment thesis. What are the exciting areas for you when it comes to investing in this domain, accelerated computing, this virtuous cycle that Eric has talked to us about? We're going to call it the Breckenfeld cycle. You all heard Dr. Breckenfeld cycle here. You heard it here first. Gilman, what are the exciting areas to invest in this domain?
So I always start with problems, right? What problem am I trying to solve? So there's some challenges within our current ecosystems. We build a semiconductor ecosystems around the large scale manufacturing of high performance chips, GPUs, CPUs, memories, right? And we run these things in the millions. We optimize our fabrication capabilities around these kind of handful of designs that we kind of pump out. And I think that's important. That's not going to go away. But I think for us to really unlock the power of microelectronics, we need to use smaller units of less complexity, in which smaller companies can innovate off of and not have to invest hundreds of millions of dollars to get to enough scale to produce this. So it requires a handful of things, in our view, that will unlock the chips ecosystem. First one is in design, right? Okay. Can we actually fully simulate a chip that we can actually apply AI in the digital twin of chip designs to speed up, because a lot of the money, quite frankly, is, there's a lot of digital design tools, but at the end of the day, you gotta do the spin, you gotta run it, you gotta test it and validate it, rinse and repeat. Every entrepreneur tells an investor, I can do it in 3 times. It's usually like 10, and it's
this is the will your chip work when it comes back? Everyone says it'll definitely work when it comes back
until it doesn't.
It often does not.
So digital design tools, digital twins, right? We're at a point where we think we're just about to get through those breakthroughs. So that's number 1.
Yeah.
Number 2, the ability to do small fab runs economically, right? And so there's lots of strategies. One strategy is to build a chiplet economy, right? You're trying to solve problems in smaller packages, right? That have standardized buses. That's like the old days, you used to stick cards in, think of it as now you're stacking chiplets in there, right? It may not be as efficient as a one big block, but it allows.
But one big block is expensive to develop.
Exactly, right. If you have the ability to do one big block, don't do it.
God does Nvidia know how expensive it is to develop one big block.
But if you have people, I'm an expert in analog design. I'm an expert in a sensor. I can build chiplets and build a chiplet economy around that. And then finally, right, we have to solve lots of problems about heat and communications, all those things. So our ability to stack high, to go from 2.5 to 3D, right, to get everything closer together, and then solving the interlink problems with optical interlinks and other strategies to make it more efficient. All those are great areas to invest in. Like that, those are things that you can make money on in the near term, not 20 years from now, right? Without having to put billions of dollars to work. And we need to do that, because if we don't develop that ecosystems, our competitor nations will. China's already going down full speed on the chiplet architecture. Why? Because they can't get smaller, because we kind of walled them off of that. So they had to come up with other strategies. And so, it's a race, and it's a race that we can win. It's a race that entrepreneurs can play and be successful and get, healthy returns for investors.
And I want to underline one note Gilman made just from a technical side. Thermal. Everything we're talking about puts stress on getting thermal energy out of these systems. And there's not easy answers to that. I mean, there are answers, they're challenging. So this is, this is as true at the individual device level with 3D stacking as it is at the data center level with trying to bring everything in the data center closer together. More density, more energy density. Even if the efficiency is better, the density is higher than the efficiency is better. That means there's more thermal energy to get out. And that's a huge challenge.
Power, space, and cooling. All right, folks, that's a wrap. Thanks to both Dr. Eric Breckenfeld from Nvidia and Gilman Louie from America's Frontier Fund for joining us today. Thanks to Keelan Wolf, Claude Jennings, and the entire NSI CTC staff for helping producing today's episode. The Control-F podcast, including this game-changing technology series, is also on YouTube. So if you want to see our faces, you want to see Gilman, you want to see Dr. Breckenfeld, you want to see me, check out NSI's page on YouTube for a video of today's episode. And make sure to join us for our next episode, where we're going to explore the opportunities and risks of the ever-evolving landscape of generative AI. And if you like what you heard or saw on YouTube, be sure to rate, review, and subscribe.